The wheel didn't just happen. Someone got mad. Someone had a really heavy rock. And someone thought, what if rolling was a thing? That's it. That's engineering. That's the whole deal. If you want to understand how humans went from dragging rocks to launching rockets, stick around because we're tearing down the myths today. Go ahead and hit subscribe so you don't miss any of our chaotic dives into how things actually get built. Because, trust me, this is going to get delightfully messy. Not magic. Not genius. Just a person with a problem and enough stubbornness to refuse to give up until something worked. And then, it didn't work. And then, it sort of worked. And then it worked, but it fell apart. And then, finally, it worked, and they probably never even wrote it down because they were too busy dragging that rock somewhere. Here's the thing about engineering that nobody tells you. It's not about having all the answers. It's about being totally fine with being wrong 17 times before you're right once. It's organized chaos. It's controlled failure. It's the scientific method with steel-toed boots and a deadline. So we've talked about physics. We've talked about chemistry. Forces, atoms, energy, the whole thing. But here's the question nobody asks in school. Okay, but what do you do with it? Like, gravity is fascinating, sure. But does knowing about gravity build you a bridge? Does understanding electron configuration get you to the moon? No. That's what engineers are for. And today, we're going inside the machine. Literally. We're going to trace how humans went from pushing rocks on logs to launching vehicles out of the solar system. And the answer is messier, funnier, and way more impressive than you think. Let's start at the absolute beginning. The bottom of the escalator. You want to move something heavy. You cannot lift it. It will not budge. What do you do? You call your friend? Oh. Your friend also can't lift it. You use a lever. You put a long stick under the rock, you put another rock under the stick as a pivot point, and you push down. The rock moves. You didn't get stronger. You didn't change physics. You just tricked physics into working for you instead of against you. That is the lever, one of the 6 so-called simple machines. And if you think calling them simple is fair after the number of civilizations they built, you're wrong. The lever, the wheel and axle, the pulley, the inclined plane, the wedge, the screw. 6 tools. 6 ways to take the force you already have and make it go further. Think about a screw for a second. What is a screw? And it's literally a ramp. A ramp wrapped around a cylinder. You spin it, and each rotation is moving you forward by just a tiny bit. But that tiny bit is carrying enormous force because the ramp gives you that mechanical advantage. A screw can hold 2 pieces of wood together against forces that would snap a nail. And it's just a wrapped up ramp. This is the thing about engineering. It keeps doing this. It keeps showing you that complicated looking stuff is just simple stuff arranged cleverly. The wheel is the same story. The wheel alone does basically nothing. What the wheel actually does is reduce friction. When you drag something, every square inch of it is fighting against the ground. When you roll it, only one tiny point touches the ground at a time. Less friction. Same force. Way less effort. And here's where physics comes back. Remember friction? Remember that surfaces at the molecular level are basically mountain ranges bumping into each other? The wheel sidesteps that whole mess. It says, I refuse to engage with your mountain ranges. I will touch the ground for 1 millisecond and move on. Genius. Petty and genius. Now zoom out a second. Because we just described the first great leap in human engineering, making physical work easier using geometry and materials. Levers, wheels, ramps, pulleys, all of these are mechanical engineering in its most ancient form. Humans figuring out how to apply force more efficiently. But here's the part where it gets interesting. Because once you can move things efficiently, you start wanting to build things. And building things introduces a completely new problem. It's not enough for something to move. It has to stay. You build a wall, it has to not fall down. You build a floor, it has to hold weight without snapping. You build a bridge, it has to survive not just the people crossing it, but the wind, the water, the vibrations, the temperature changes, the fact that some guy decided to drive a fully loaded truck across it at 3 a.m. This is where civil engineering enters the chat. Civil engineering is the art of making structures that don't fail. And the word art is not an accident, because a huge amount of early civil engineering was genuinely artistic intuition. The Romans didn't have calculators. They didn't have stress analysis software. They didn't have textbooks explaining the load distribution of an arch. They just built a lot of arches until the arches stopped falling down. And wait, that's the part you need to hold on to, because we're going to need it later. Whoa. The arch is one of the most beautiful accidents in human history. Early builders tried flat stone lintels across openings. Think Stonehenge. Think ancient doorways. Flat stone across two upright stones. Works fine for small spans. Try to go wider, and the stone cracks in the middle. Why? And because flat horizontal beams experience bending, the top gets compressed and the bottom gets stretched, and stone is terrible at being stretched. Stone is strong in compression. It is embarrassingly weak in tension. So how do you build wider openings without snapping your stone? You stop fighting the physics and let the physics solve the problem for you. You curve the stones upward. You make an arch. And suddenly, all the forces in that curved structure get redirected downward and outward into compression, the thing stone is actually good at. The Romans didn't fully understand why this worked. They just noticed that it did. They built thousands of arches. Some fell. Most didn't. The ones that didn't fall are still standing 2,000 years later. The Pont du Gard Aqueduct, the Pantheon, the Colosseum, built by people who understood the principle empirically, meaning they figured it out by doing it, not by deriving it mathematically. That's the method. That's been the method since the beginning. Try it. Watch what breaks. Understand why it broke. Fix it. Repeat. Engineers have a name for this. It's called iterative design. And honestly, the more elegant name they have for the same process is trial and error. Fast forward about 15 centuries. You've got the arch, you've got stone, you've got wood, and suddenly you've got steel. And everything changes. Steel does something stone physically cannot. It handles tension. It can be stretched, bent, pulled, and it springs back. It can be formed into cables. And a cable in tension is basically the arch flipped upside down. Instead of pushing forces into the ground through compression, you're hanging things from above through tension. This is the suspension bridge. The Brooklyn Bridge. The Golden Gate. The cables are arches running in the opposite direction, doing the same fundamental job. And here's the plot twist. A suspension bridge and a Roman arch are the same concept. Compression and tension are just opposite sides of the same force. Two things that look completely different. Same physics. Disguised. Okay, but now here's the midpoint. Stop scrolling. Put the phone down. Well, not down, you need it to watch this. But mentally, stop. Because this next part actually should make you a little dizzy. Wow. The Burj Khalifa is 828 meters tall. It weighs roughly 500,000 tons. It stands in Dubai, which sits on sand and soft sedimentary rock. And it does not sink. It does not tip over. It does not vibrate itself to pieces even though winds at that height hit around 150 kilometers per hour. How? The foundation goes 50 meters into the ground. That's a 16-story building worth of concrete and steel just shoved underground so you can't see it. The structure uses a buttressed core design where 3 wings extend outward and each one stabilizes the others, like 3 people standing back to back so none of them falls. The shape tapers as it rises, reducing the surface area the wind can push against. And engineers knew all of this, not because someone magically figured it out, but because before they built it, they tested a small model of it in a wind tunnel for months. They ran simulations. They calculated stress loads. They changed the design over a dozen times. There is no final answer in engineering. There's only the current best answer under current constraints. Now here's where it gets multi-dimensional. Because civil engineers need structures to stand up, but mechanical engineers need things to move. And move precisely. And move repeatedly without wearing out. Think about a car engine. What is actually happening in there? You're taking gasoline, which is stored chemical energy, and you're exploding it inside a cylinder. That explosion pushes a piston down. The piston connects to a crankshaft. The crankshaft rotates. That rotation eventually gets to your wheels. You've converted chemical energy into linear motion, into rotational motion, into vehicle movement in about 1/10 of a second. That conversion chain, energy changing form to do work, is mechanical engineering in its purest state. Thermodynamics, friction management, material fatigue, fluid dynamics, all of it crammed inside a package the size of a suitcase, running thousands of times per minute, expected to last for a decade. And when something goes wrong, when there's a rattle, a leak, a weird vibration, the engineer's first tool isn't a textbook. It's their ear. Tap the pipe. Listen to the engine. Feel the vibration with your hand. Then go to the math. Diagnosis is intuition first, analysis second. And that intuition gets built through, say it with me, trial and error. Now hold that thought about engines. Because there's a field that took the engine, pointed it at the sky and said, what if we just kept going? N. Gravity doesn't go away when you're in a plane. That sounds obvious. But think about what a plane is actually doing. It is a metal tube weighing up to 400 tons hurtling through air at 900 kilometers per hour. The air is thin. It is cold. The engines are essentially controlled explosions happening continuously at the front of metal cylinders. And somehow this whole thing doesn't just fall. Why doesn't it fall? And? Lift. And lift is the thing that makes aeronautical engineering feel like cheating. Here's the question. Why does a wing produce lift? You've probably heard the Bernoulli explanation. Air moves faster over the curved top of the wing, lower pressure above, plane gets sucked up. That's partially true and mostly oversimplified. What actually creates lift is more interesting. A wing pushes air downward. That's it. By Newton's third law, every action has an equal and opposite reaction. If the wing pushes air down, the air pushes the wing up. The wing is throwing air at the ground and riding the recoil. Which means flight is basically the world's most elegant, controlled fall. You are always falling. The wing just keeps throwing air hard enough to counteract it. The Wright brothers understood almost none of this mathematically. What they had was a homemade wind tunnel, literally a box with a fan, and they tested over 200 different wing shapes in it over 2 years. They flew because they out-tried everyone else. First successful flight, 12 seconds. 36 meters. A distance shorter than the wingspan of a modern 747. Wow. 66 years later, humans landed on the moon. Let that ratio hit you for a second. 12 seconds of wobbling 12 feet off the ground. 66 years. Moon. Aerospace engineering is what happens when you take every branch of engineering and stack them on top of each other under extreme conditions. A space rocket is mechanical engineering because it has engines and moving parts and pumps. It's chemical engineering because the propellants are precise reactive compounds. It's electrical engineering because the guidance systems, computers, and sensors run on carefully managed electronics. It's thermal engineering because re-entry generates temperatures over 1600 degrees Celsius, and you really don't want the astronauts to notice. And this brings us to electrical engineering, which quietly runs everything and gets zero credit. Electricity is the invisible infrastructure of the modern world. Every machine we've talked about, the car engine, the airplane, the skyscraper, has an electrical system keeping it alive. Sensors, actuators, power management, communication. All of it runs on controlled electron movement through circuits. And here's the weird thing about electrical engineering. You can't see what you're working with. A mechanical engineer can look at a cracked beam. A civil engineer can see when a wall is leaning. An electrical engineer is essentially debugging an invisible river. The electrons are moving, or they're not, and you figure out what's wrong by measuring voltages, checking resistances, tracing signals. The running joke in electrical engineering is that when all else fails, you wrap it in blue electrical tape and pray. That's not entirely a joke. There's a very real culture in engineering of the good enough patch, the fix that isn't elegant, isn't pretty, but gets the system running while you figure out the real solution. NASA's Apollo 13 crew survived partly because ground engineers improvised a carbon dioxide filter out of a sock, a plastic bag, cardboard, and duct tape in under an hour. That's not a failure of engineering. That's the whole point of engineering. The whole point is that the world is not a controlled lab environment. Things break in unexpected ways. Constraints change. Resources run out. Deadlines arrive. And the engineer's job is to solve the real problem with what actually exists, not the theoretical problem with infinite resources. Which brings us back to where we started. A person. A heavy rock. Not enough force, not enough time, definitely not enough equipment. And the question, what can I build right now with what I have that makes this work? And that's been the question since the first lever. It's still the question at NASA, at Boeing, at every construction site, every server room, every car factory on the planet. The tools have changed. The math has gotten incomprehensibly powerful. But the method? Trial. Error. Adjust. Repeat. And maybe a little blue electrical tape. Here's your awe out. Everything you interact with today, every bridge you've crossed, every building you've been in, every screen you're looking at, every vehicle that's ever carried you, was at some point a problem that a person sat down and decided to solve. And they were probably wrong the first time. And the second time. And they kept going anyway. Now here's the question that nobody has answered yet. As we build systems that are too complex for any single human to fully understand, AI networks, global power grids, quantum computing architectures, who is responsible when they fail? N? When the system is smarter than its engineers, and something goes wrong, do we still get to call it engineering? N? We don't know yet. But someone's already building a lever to find out. If an AI-designed bridge collapses, who goes to jail? The programmer who wrote the algorithm, or the engineer who blindly trusted it? N. Let me know your thoughts in the comments below, because this is a debate we're going to have to settle sooner than you think. And if you enjoyed today's journey through human stubbornness, make sure to subscribe so you're here for the next one.